I want you to do something with me right now. Hold your phone out at arm's length, and try to move it left, then stop it dead. Feel that? That stubborn refusal to change motion isn't. Wait. It's something deeper. It's mass showing up as a sensation. And here's the punchline. The best explanation we have says empty space is involved. You're not in a lecture hall with me. You're in a lab mindset, right here, right now, turning your own muscles into instruments. The phone is ordinary. The air is ordinary. Your hand is ordinary. But the feeling you just noticed is not an everyday fact. It's a clue. Because the universe gives different objects radically different personalities when you try to push them. A feather and a brick both fall in the same gravitational field if you remove air. But try to accelerate them, try to make them change their motion, and the brick feels like it's anchored to a deeper law. The feather yields. The brick argues. And light? Light doesn't just yield. Light races. Photons don't get tired. They don't hesitate. In vacuum they move at one speed, always, as if the universe has written a rule in permanent ink. You, light, do not get to slow down. So the human question is visceral. Why do some things feel stubborn to move? Why does matter drag its feet while light slips through reality like it owns the place? Now a trap. A very common one. We hear mass, and we think gravity. We think heaviness. But heaviness is what you feel when gravity tugs on you and the floor pushes back. That's weight. We can change it by going to the moon. We can remove it by going into orbit. Yet your mass, your resistance to acceleration, follows you everywhere. So our investigation, the audit, has a strict scope. We are not asking, why do things fall? We're asking, why do things resist being pushed? Why does the universe demand a price for changing motion? And I'm going to make a promise that sounds almost offensive to common sense. Before we're done, we will treat empty space like a suspect. Not as a stage. Not as a passive nothingness where the real drama happens. As an active participant. We will stress test the idea that the vacuum, what you call nothing, quietly sets the rules that decide who gets to have mass and who must remain massless. But we're going to do it like scientists. We're going to keep asking, what can we measure? What do the equations demand? And where are the myths hiding, waiting to ambush our intuition? So here's the operational starting line, the kind you can build an experiment around. Mass shows up in two ways that look different until relativity forces them to shake hands. First, inertia. If you push on something with a force F and it accelerates with acceleration A, the ratio is mass, F equals m times A. Mass is the conversion factor between push and response. It's how much motion change you buy per unit force. Second, rest energy. Einstein's E equals mc squared. That equation is famous enough to be printed on coffee mugs, which is a strange fate for a statement about the deep bookkeeping of reality. But what it really says is this: even when something is perfectly still, if it has mass, it is storing energy just by existing. Not chemical energy. Not battery energy. A deeper, locked-in budget, rest energy. And in relativity these aren't two separate meanings. They are two faces of the same coin. Inertia and rest energy are both ways the universe keeps track of how matter fits into space-time. If you change the energy of a particle, you change how it moves. If you change how it moves, you change its energy. The old split. Mass is how hard it is to push, versus mass is a kind of energy, turns out to be one unified story told in two dialects. But we're not done, because physics has a habit of answering one question by revealing a bigger one behind it. Okay, mass measures inertia. Inertia is tied to energy. But what sets the value of that mass? Why does an electron have the mass it has? Why is the top quark so much heavier than an up quark, like nature dialed one knob to whisper and another to shout? To go further, we have to zoom in past the objects in your hand and into the cast of the Standard Model. And I want you to picture this not as a zoo of tiny billiard balls, but as something stranger and more beautiful. A universe made of fields. A field is a rule spread across space. Like temperature in a room, you can point to any location and ask, what's the temperature here? You don't need a temperature particle, to exist at every point, you have a property assigned everywhere. Quantum fields are like that, except they can vibrate in discrete packets. Those packets are what we call particles. So the standard model is a roster of quantum fields that fill all of space all the time. Quark fields, electron fields, neutrino fields, and fields for forces, electromagnetism, the strong force, the weak force. When a field gets excited, it produces a particle, an electron, a photon, a quark, like a guitar string producing a note. The thing is the vibration. The substance is the behavior. Now, here's the problem that used to haunt physicists like a recurring nightmare. In the equations, the weak force, the one responsible for radioactive decay and some of the most important nuclear transformations in the cosmos, behaves in a very delicate way. It has a symmetry structure that makes the math consistent, predictive, and in agreement with experiments. But that symmetry, if kept intact in the most straightforward way, insists that the carriers of the weak force should be massless. Massless like photons. But in the real world, the weak force is short range. It dies off quickly. It doesn't reach across galaxies like light does. And in quantum field theory, short range is the signature of massive force carriers. The W and Z bosons are heavy. We measured that. Nature didn't ask our permission. So we were stuck. If we gave the W and Z bosons mass by brute force, just add mass terms into the equations, the beautiful symmetry that made the theory work would fracture. Predictions would blow up. The math would lose its grip on reality. It's like trying to repair a watch by hammering the gears into place. It might tick once, but it won't keep time. At this point, you can feel the tension the way those mid-century theorists must have felt it. You have a theory that seems to know something true about nature, and nature is doing something that seems to violate the rules of your theory. Who's wrong? The equations? The experiments? Or your assumption about what, empty space, is allowed to be? So imagine we're in that era. It's the early 1960s. Chalk dust. Cigarette smoke. A blackboard full of symbols that look like a language spoken by reality itself. And someone has a thought that feels almost scandalous. What if the vacuum isn't symmetric? What if empty space is not the zero setting of all fields? What if one field, quietly, has a non-zero value everywhere, even in the deepest dark between galaxies? That idea is the seed of the Higgs mechanism. And I want to be careful here, because the popular story, "Particles move through molasses and get heavy," is catchy and mostly misleading. It conjures friction. It suggests energy loss. It makes you picture particles plowing through a syrupy medium. But the Higgs field is not sticky. It doesn't slow particles down by dissipating energy. A better way to picture it is social, not viscous. Think of walking through a crowded room. The room isn't filled with glue. Yet depending on who you are, you might get stopped constantly. People call your name, ask you questions, pull you into conversations. Or you might slip through nearly untouched. The resistance isn't from syrup. It's from interactions. Probability. Connection. So the Higgs field is a universal field. It exists everywhere. And it sits in a particular state, the vacuum state, that is not zero. This is the crucial twist. The vacuum can have structure. Empty can have a background value, a kind of quiet order. In physics language, it's called a vacuum expectation value. That phrase sounds like bureaucratic paperwork. But the concept is intimate. It's the value a field prefers to have when nothing is exciting it. Its resting posture. Now here's the move that changes everything. Certain particles interact with the Higgs field. That interaction changes the relationship between their momentum and their velocity. It changes their energy bookkeeping in such a way that, in the equations, they behave as if they have mass. Not because a literal substance got stuck to them, but because the rules of motion in the presence of that background field include an effective mass term. If that felt abstract, good. It means you're taking it seriously. Let's give your intuition a handhold. Picture a landscape with a hidden slope. At first glance it looks flat. You step forward and you expect effortless motion. But after a few steps you realize you're climbing. The effort isn't because the ground is sticky, It's because the terrain has shape. The Higgs field is like a terrain in field space. Its non-zero vacuum value means the flatness you assumed for empty space is a lie. And there's a second analogy that helps: a tuning fork. In air, a tuning fork can push on the air and make sound waves. In a vacuum chamber, it still vibrates. The fork hasn't changed, but sound propagation changes because the environment changes what behaviors are possible. The medium doesn't create the fork, it changes the dynamics available. The Higgs field doesn't create particles out of nothing, it changes what motion relationships are allowed for them. Now we reach the subtle centerpiece: symmetry. In everyday life, symmetry is aesthetic: balanced wings, mirrored patterns. In physics, symmetry is a rule about what transformations leave the laws unchanged. Rotate a perfect circle and nothing changes. That's symmetry. The electroweak theory has a symmetry that, if kept unbroken, implies massless W and Z bosons. But what if the laws are symmetric while the vacuum is not? This is like a perfectly symmetric pencil standing on its tip. The laws don't prefer it to fall in any direction. But the moment it falls, it picks a direction. The symmetry of the underlying rules remains. The state you end up in does not display the symmetry. That's spontaneous symmetry breaking. Again, the phrase is dramatic. The mechanism is quiet. The universe chooses a vacuum state that isn't symmetric in the same way the equations are. And when it does, something extraordinary happens. Some of the degrees of freedom in the Higgs field effectively become the longitudinal components of the W and Z bosons. The weak force carriers acquire mass without us having to smash the symmetry with a hammer. The theory stays consistent. The infinities behave. The predictions survive. And the particles we call electrons, quarks, and others, some of them coupled to this Higgs field too. That coupling determines how strongly they talk to the Higgs background, and that strength shows up as their masses. It's not the only contributor to the mass of everything you touch, but it is the reason many fundamental particles can have rest mass at all within the Standard Model's rules. At this point, someone always asks, so is the Higgs field responsible for gravity? Does it make weight? No. That's a myth wearing the costume of a deep question. Gravity, in general relativity, couples to energy and momentum, basically to the stress-energy content of the universe. The Higgs mechanism explains why certain particles have rest mass. That rest mass contributes to the energy budget, sure. But gravity doesn't privilege Higgs-given mass over other forms of energy. A hot gas gravitates more than a cold one. Binding energy gravitates. Pressure gravitates. Light gravitates. Another myth: all mass comes from the Higgs. Also no. In fact, most of the mass of you, and me, and your phone, lives in protons and neutrons. And most of the mass of a proton is not from the Higgs-given masses of its quarks. It's from the energy stored in the strong force, the gluon fields, and the kinetic energy of quarks trapped in a tiny quantum prison. It's a storm of QCD, the strong interaction, converting energy into mass via E equals mc squared. So why does the Higgs matter if it doesn't account for most everyday mass? Because without it, the Standard Model collapses into a different universe. Quarks would be massless in the simplest version. Electrons would be massless. And massless charged particles behave in ways that tear apart the chemistry we rely on. The Higgs field is not the whole story of why your body weighs what it weighs, but it is part of the story of why matter can form stable atoms the way it does. And one more myth to kill cleanly: the Higgs field isn't molasses. It doesn't create drag. It doesn't make particles lose energy as they move. If it did, everything would slow down and heat up and the universe would be a very different place. The Higgs changes the relationship between momentum and velocity, like changing the rules of how a given push translates into a change in motion. That's why inertia feels like a property of the object, even though, at the deepest level, it's a property of interaction with a field that fills space. Now let's do the stress test. Slow down with me. Imagine a dial we can turn, the value of the Higgs field in the vacuum. In our universe, that value is not zero. It's about 246 giga-electronvolts in the language of particle physics, but don't get lost in the units. What matters is, it's a constant background, a frozen posture of the field. Now we turn the dial to zero. We create a hypothetical universe where the Higgs field does not take on that non-zero vacuum value. What survives? What fails first? At first it feels like a small change. After all, empty space being more empty sounds like it should simplify things, not break them. But here's what happens. Without that non-zero Higgs vacuum value, the electroweak symmetry remains unbroken. The W and Z bosons become massless. The weak interaction becomes long-range in a way it is not in our universe. The delicate balance of nuclear processes changes. Stars, if they form at all, would burn differently. Then you look at electrons. If the electron is massless, the way it binds to nuclei changes profoundly. Atoms are not just little solar systems. They are quantum standing waves. The electron's mass sets the scale of the Bohr radius, the size of atoms. Change the electron mass, and you change chemistry's ruler. If you remove it entirely, the very notion of an atom as we know it is in jeopardy. Would there be matter, in any familiar sense? Maybe there would be fields and interactions, and maybe there would be bound states of some kind. But the stable, roomy, chemically rich architecture that allows molecules, water, proteins, and brains, this is not guaranteed. The Higgs vacuum value is not a decorative constant. It is one of the quiet settings that makes our kind of complexity possible. Now comes a paradox that is less about equations and more about lived experience. If mass is an interaction with a field, why does it feel intrinsic? Why does an electron always carry the same mass? Why doesn't pushing it harder change its mass like shaking water off a wet dog? The answer lives in the word vacuum. In quantum field theory, the vacuum is not nothing. It's the lowest energy arrangement of fields, a kind of ground state. Think of a crystal lattice at absolute zero, not dead, not absent, but ordered. The quantum vacuum is like that, a structured baseline with rules, fluctuations, and measurable consequences. When a particle couples to the Higgs field, it couples to that baseline value everywhere. It's not carrying around bits of Higgs like luggage. It's living in a universe where the background field is always present, like a fish living in water, except the fish doesn't push water aside to create mass. The water sets the conditions. The equations of motion inherit an effective mass term because the background is constant. And pushing the particle harder doesn't shake off that coupling because the coupling is part of the field's identity. It's a parameter in the underlying theory, like an electric charge. You can accelerate an electron until it's nearly light speed, and what changes is its energy and momentum, not its intrinsic coupling to the Higgs background. Relativity will make it harder and harder to accelerate further, but that's not the Higgs adding syrupy drag. That's spacetime's own accounting system, insisting that you can't push a massive particle to the speed of light without infinite energy. Now, history. Because ideas like this don't arrive with trumpets. They arrive with suspicion. In the 1960s, several groups of theorists, Higgs, Brout and Englert, Guralnick, Hagen, and Kibble, circle around the same daring mechanism. They're not writing poetry. They're trying to save a theory from mathematical disaster. They propose that a scalar field with a non-zero vacuum value can give mass to gauge bosons while preserving a consistent quantum theory. But proposing is not proving. And nature is under no obligation to honor our cleverness. For decades the Higgs field is an inference, a ghost in the equations. If it's real, it should have an excitation, a particle, a ripple, a quantum of the Higgs field itself. That ripple is what we call the Higgs boson. Notice what that means. The Higgs boson is not the thing that gives mass. It's evidence that the field exists, because fields that fill space can be excited like any other. If you can ring the field like a bell, you can detect the ring. That's the boson. Now bring yourself to CERN, to the Large Hadron Collider era. You're not watching a neat Eureka! Scene. You're watching years of building, calibrating, and doubting. You're watching teams who know that nature hides behind statistics. You're watching detectors that are less like cameras and more like vast, layered instruments, silicon trackers, calorimeters, muon chambers, each one translating violence into data. And the violence is precise. Protons whipped to near light speed collide, converting kinetic energy into showers of new particles. Most of those events are boring in the way that 1 million lottery tickets are boring. They're mostly background. The Higgs, if it appears, will not stand up and announce itself. It will vanish almost instantly, decaying into other particles, 2 photons for leptons, bottom quarks, leaving signatures that mimic many other processes. So you search for a bump, a subtle excess, a hill in a landscape of noise. And when that bump appears, around 125 electronvolts, what you feel isn't philosophical closure. It's something more human, relief mixed with fear. Relief that the decades-old mechanism might be right. Fear that you might still be fooled by statistics, by calibration errors, by your own desire for the story to end neatly. And then, after cross-checks and more data and independent confirmations, the signal holds. The Higgs boson is announced. Not as, "We found the meaning of mass," but as, "We found evidence for the field structure that allows the standard model to be self-consistent and match reality." That is a quieter sentence. It is also a more honest one. So, case closed? Empty space gives things mass, we go home? Not even close. Because the moment you confirm the Higgs, you shine a harsh light on the edge of our understanding. And the first thing you see is a problem with a name that doesn't sound scary enough: naturalness. The hierarchy problem. Here's the essence without the algebra. Quantum fields fluctuate. And those fluctuations correct particle masses. For most particles, symmetries protect their masses from exploding to enormous values. But the Higgs is a scalar. Its mass is unusually sensitive to quantum corrections from very high energy scales. The math suggests it wants to be much heavier than it is, maybe up near scales associated with grand unification or quantum gravity, unless something cancels those corrections with exquisite precision. So why is the Higgs mass about 125 GeV and not, say, a trillion times larger? Is it a coincidence? Is it fine-tuning, nature balancing contributions to many decimal places just so we can have this particular world? Or is there new physics, supersymmetry, compositeness, new dynamics, that stabilizes the Higgs naturally, waiting beyond the energies we've reached? This is where intellectual rigor demands humility. The Higgs mechanism explains how particles can get mass without breaking the mathematical consistency of the electroweak theory. It explains the how, at the level of mechanism. It does not explain the deeper. Why these numbers? Why these couplings? Why this vacuum value? Why this pattern of masses across generations? And that's not a failure. It's a map. Physics is a series of rooms. You open one door and you find a deeper hallway. The Higgs opened a door into the architecture of the vacuum. But it also revealed that our house may have an unseen foundation. Now bring it back to your hand, back to the phone, back to the lived sensation that started this whole investigation. You're holding an object in a universe of fields. When you tried to change its motion, you feel resistance. That resistance is not just stuffiness. It's the translation of field relationships into muscle strain. Your mass, your inertia, is part of how your matter negotiates with the rules that fill all space. And once you see that, the old picture of reality, little solid beads moving through emptiness, starts to look like a useful cartoon. The deeper picture is relational. Because what is a particle, really? In the standard model, it's an excitation of a field. It's a localized pattern of energy and momentum. Substance is not a primitive ingredient, it is an emergent behavior, stable patterns that persist because the rules allow them. That's why the vacuum matters. The vacuum is not absence. It is a state. A state with symmetries, with background values, with fluctuations, with consequences. The cosmos has a texture even when it looks perfectly still. If you want a single sentence to carry out of this video, it's this: empty space is not the stage, it's part of the script. And we can now make the cleanest takeaway, without myths. The Higgs field does not make things heavy in the sense of gravity. It makes many particles capable of having rest mass at all within the electroweak theory's consistent structure. Meanwhile, most of the mass of everyday objects comes from energy trapped in the strong forces choreography inside protons and neutrons. The universe is not heavy because it's full of stuff. It's heavy because energy can knot itself into stable patterns, and because some of those patterns interact with a field that never turns off. So here's the contemplative thought experiment I want to leave you with. Imagine you could reach into the vacuum, not add energy, not remove matter, but change the state of the fields themselves, the baseline rules. How many properties you think of as intrinsic, mass, charge distributions, maybe even the flow of time as experienced by matter, would quietly change without anything touching you? And then, the next door. If mass can be an interaction, if stubbornness against acceleration can be a relationship with a field, what else that feels intrinsic might be relational to? Your sense of time. Your sense of identity. Even your intuition that nothingness is simple. We step away from the whiteboard now. The room looks the same. The air doesn't shimmer. Your phone still feels stubborn when you move it. But the emptiness between you and the walls should feel different, less like a void, more like a presence. A quiet set of rules, holding the universe in a particular posture. If you want to keep going, there's another video on the end screen that picks up this thread and pushes it into the next frontier. Watch that next, because it's the fastest way to stay inside the same chain of questions. And if this changed how you feel about empty space, subscribe, not for notifications, but because this channel is an ongoing audit of the stories we tell about reality versus what the evidence actually permits. One last question for you, simple, and I genuinely want your answer in the comments. When you think about mass now, does it feel more like a thing you possess, or a relationship you're participating in?